Welcome to EDU World Space.
So we are given a sequence Tn defined by the following. So here we have a partial sum of the harmonic series, the first n terms, and then we subtract natural log. Now for part A, we like to go ahead and show that this is always positive. Okay, and so here's how we can do this. So let's look at Tn here, and I want to interpret this, at least the first part here, let's say in blue, as areas of rectangles. So the first one, I'll put a rectangle of height 1 corresponding to the first term 1, and I'll put it here at n equals 1 to 2. And this way the area of the rectangle is my first term. Second rectangle, height will be a half for the second term, and so on. And then the very last one would start at n to n plus 1, and that would have height 1 over n. However, let's also look at 1 over x. And the reason I'm looking at 1 over x is because we'll see in a second, well, if we integrate this, so here if I look at 1 over x in green, if I were to graph that, this one will have area less than, because it's always either on or below the boxes, so this number here is strictly less than if you're looking at it in terms of areas. So what that means is we can write the following. So just focusing on parentheses, we just showed that this is larger than, and by simplifying the integral here, as we just saw a moment ago, this is just ln minus ln n. And there we go. As a consequence of our work here, we have Tn larger than 0. And that resolves part A. Now let's go on to part B here. So here we want to interpret the difference interpret this as a difference of areas. To show that the sequence Tn converges. Okay. So first of all, let's just verify this expression here. Okay, so now after we subtract, we could cancel these, and then watching out for the minus signs here, we'll have ln n plus 1 minus ln n minus 1 over n plus 1. So now let's go ahead and follow the advice here. Let's interpret this as an area. So first, let's just focus on the first term. And so what we mean here is let's go ahead and replace this with the integral. And since n goes to infinity, we can integrate from 1 to infinity ln x plus 1 minus ln x. Similarly, if we interpret 1 over 1 plus n as an area, then the corresponding integral should be 1 to infinity 1 over x plus 1. Going on to the next page, then the interpretation of the difference of the areas is interpreted as integral 1 to infinity, and now we just subtract. Now, there will be some cancellation between these two integrals a little bit. So instead of worrying about the limits of integration, let's just ignore those for a second. So ignore the limits of integration just for the time being, so temporarily. We'll bring these in at the end. We don't want to have to use L'Hopital's rule if in one integral if we're going to have to do the same exact argument in the second integral and the terms end up canceling out. So first, let's just focus on this indefinite integral here. Here we use integration by parts, IBP, and you would go ahead and just take u to be, and actually in this case, let me actually take a step back before I integrate this. This one will be better if we write this as 1 logarithm, or even better, 1 plus 1 over x. Now go ahead and do integration by parts here. Take your u to just be the integrand, which forces dv to just be dx. So if you do this integration by parts here, then you'll get the following. And similarly, the second integral, including the sign here, this is just negative. And this is exactly why we wanted to ignore the limits of integration first. Now we could cancel those and then just take the limits of integration to this guy. So going on to the next page. So first, let me take a step back to just mention what I did here. So first of all, we just showed this. The interpretation of the change in integrals after doing integration by parts for the first integral, we arrived at this term here. Was where the IBP came from, and then the second integral, and then we canceled, and now we just have. However, instead of doing the indefinite integral, we really should be looking at this integral here. So what we'll do is write that infinity as a limit. Since we've already integrated, now we just use the integrand here, or the answer here. And then t is going, or x is going from 1 to t. So plug in the t. And then if t is 1, you just get ln2 there. And then this is in the limit. This is the form infinity times ln of 1, which is 0. So this is indeterminate, so we should prepare ourselves to use L'Hopital's rule. So what I'll do here is write the negative ln 2 out there, and then I'll write this limit as ln over 1 over t. Now, this is of the form 0 over 0 as t goes to infinity, so use L'Hopital's rule here. Derivative of the top, 1 over 1 plus 1 over t, use the chain rule with the power rule there, and once again using the power rule down here, but luckily these two terms cancel out from the chain rule, and as t goes to infinity, this will just go to 1, so we just have 1 minus ln 2, which is about 0.307. So going on to the next page, we conclude the difference in areas as n goes to infinity is positive. And we have another remark here, ln n plus 1 over n is always positive and is increasing, since the natural log is increasing. As x gets bigger, the natural log gets bigger. If n gets bigger, then this fraction gets bigger, and that ultimately means the log is getting bigger. Okay, so also we have both areas are positive as n goes to infinity, because we have the same remark here for 1 over n plus 1. This is positive but decreasing. And now we showed that the difference is approaching a positive number. And what this ultimately means is that Tn minus Tn plus 1 must be larger than 0. And that means that this is a decreasing sequence, because if you just push the Tn plus 1 to the other side, you have this, and that's exactly what it means to be decreasing. And that resolves part B.